So I'm going to tell some stories and give some perspectives on my experience in the last 10 to 15 years helping to define and to execute so-called modern simulation programs within various agencies of the DOE as well as within the lab. So I'm going to speak at a very high level, and one thing that is particularly interesting is in spite of all of the deep technical challenges, there have also been much higher level challenges that have stalled progress in areas that I would like to see improve going forward. And they come from a lack of clarity and a lack of common understanding in what we're even trying to do. So I thought this would be a fun forum to discuss some of those issues. And I'll start very, very simply. And I'll say that one of the big issues is when we talk about computer simulation, there's considerable confusion and considerable lack of common understanding about what we're even talking about. And this causes all sorts of misunderstandings and lack of progress in areas where we could move forward much more quickly. So let me just pose a couple of very simple questions. I want to ask what we mean by computer simulation generally and specifically applied to the field of nuclear energy. What's its principal goal, and what are its ultimate potential and its inherent limitations? And those questions sound very simple, but they're not quite as easy as they seem, okay? And the way I want to start doing it is with a drawing, and I whipped this up myself in PowerPoint a few days ago, and I want to give a second to explain it. So there are a few axes. Let's see, there are three axes. On the x-axis, I'm plotting the universality of the physical laws that we are either trying to solve as maybe a differential equation or whatever expression of them that we have. But we can imagine them being very specific to a particular device or a particular geometry or a particular reduced set of physics, or we can imagine them being much more general. So that we have on the x-axis. On the y-axis, I have the accuracy of the methods. This is very notional. This is not meant to be precise. You could argue with these bubbles, and they depend on almost everything, but I think the concept is important. And then on the z-axis is the predictive range. So the predictive range would mean how much can I go from a scenario that I've already studied experimentally or that I know the answer to something that looks different. Okay, can I change a couple of small parameters? Can I completely change the geometric configuration? And anyhow, in that three-dimensional space lie very different techniques, all of which people generally refer to as computer simulation. And this is sort of the beginning of a lot of misunderstandings. So on the one hand, I'll start in the upper right. This is what we endeavored to do starting 15 years ago or so in a modern simulation program, was mechanistic modeling. And of course, none of these is perfectly clear. Most things are some kind of hybrid. But with mechanistic modeling, we're endeavoring to solve a system of equations that universally describes the phenomena that we're looking at. So whether it's the transport equation for neutron populations or the Navier-Stokes equation for fluid momentum or heat transfer, the idea is that they're not specific to the situation that we're looking at. In the middle are hybrid models, which contain some degree of universal physics formulations and some degree of calibration or parameterization specific to what we're looking at. And as we move to the left, we have empirical models where they are much more representations of things that we learn from experiments that are turned into fairly simple functional relationships, or even things that are simpler, which is doing experiments and interpolating between data points. Okay, so obviously computers are used for all of these different activities, and depending on who you talk to, they'll consider one or the other to be a form of computer simulation. So to be very clear to start, we, in launching the original sort of next generation of nuclear energy advanced modeling and simulation programs, we're aiming to the greatest extent possible to use modern techniques and modern hardware to move much more toward mechanistic models and away from empirical models, which had been the bread and butter of nuclear energy design and analysis for 30 or 40 years. And of course, the truth is much murkier. There's sort of everything in between, but That's a simple conceptual framework. And of course, I want to emphasize that mechanistic models in no way can be considered more accurate for all problems than empirical models could be. So I put it a little lower on the y-axis. But there are a few things we have to realize. Issue number one is there is a very strong, very intimate connection between mechanistic modeling and high-performance computing. And I think the reason is obvious, and that is when you break a system down to that many subcomponents, it becomes a massive compute-intensive problem. And I'll give examples different from the ones I've heard this morning. Just for the fun of it, I give many. So one of the great challenges that I've worked on for the past 7 or 8 years, mostly with Cord Smith and company at MIT, is to do point-wise energy, whole core Monte Carlo neutron transport of a reactor core. It's a harder problem than we realized. We're talking tens of billions of neutron histories, a terabyte or more of tally data, 100 gigabytes of point-wise cross-section data that every single processing element needs fast access to. It's a massive problem beyond the reach of actually what we can do on modern leadership compute platforms. But you see why there's such a strong connection. Another would be channel resolving computational fluid dynamics, even something which is known as large eddy simulation, which adds a little modeling for the unresolved scales. So we're talking billions or more of mesh elements, very long integration times to be able to get stable estimate or accurate estimates of statistical quantities. So immediately, when you recognize the scale of the computational problem for doing mechanistic modeling, it is tightly tied into both research and all of the techniques and knowledge that we've gained from high-performance computing. Okay, so one thing that is also not very clear that needs to be emphasized is what is the role of mechanistic models and how do we endeavor to use them? The easiest way to think of this from a high level, which is very different from empirical models, is that we want to think of mechanistic models as close as possible to actual experiments. Of course, they're not. There are different issues. There's floating point representation. There is the lack of ability to truly resolve everything. But at their heart, they are the closest cousin to true experiments and much closer to that than, say, they are to empirical models or certainly curve fitting. And I show a bad picture here of looking down on a reactor core, the neutron density from a Monte Carlo transport simulation. And one of the classic problems is depicted on the right, which we've learned the hard way, is it converges much, much slower than we ever anticipated. So the 1 over square root of n is the nice line that none of the curves adheres to. And the interbatch correlations slow it down. So it's a massive problem. But if you can do it, you tend to think of it as fairly close to what you would get out of an experiment, modulo a whole other set of things that are, relatively small compared to if you were looking at empirical models. So let's talk about the role of empirical and hybrid models. It's very, very different. Okay, the role of an empirical hybrid model is to act as a design tool. So it has to be fast and it has to be robust. And when I say robust, I mean for a given set of inputs, you need a set of outputs, which is your answer. And you have to be able to do many scenarios. You have to be able to do them very quickly. And you have to be able to get an answer for every scenario that you're looking at. So the role is very, very different because when you're doing mechanistic modeling, you haven't finished your job when you've done the simulation. It's the same as doing an experiment. You have all of the creative and difficult questions that you would have to ask about how you would use experimental results when you do a mechanistic simulation. You don't do it and get an answer and you are done. It's a very, very different mode of computing. And as was pointed out in an earlier talk, there's a relationship between the two, and it's not an adversarial relationship. Okay, the relationship is that these numerical experiments or mechanistic modeling really yield a form of data sets. And the data sets can be used to improve the empirical and the hybrid models. Okay, so you don't think of a reactor designer sitting in front of a supercomputer and doing a 3-day simulation on an exascale machine and deciding to change some aspect of the configuration based on what they learned. That might happen at a very, very, very late stage of design. But typically speaking, what you learned, you would put into an empirical or hybrid model that needed to be robust and that was used for fast turnover design analyses. Other reasons might be for the final stage of a detailed design evaluation, or maybe at a certification or qualification stage. So it's incredibly important to be clear about that, because all of the confusion with the definitions and the concepts makes it very hard to put together a program that can move forward technically. Okay? So this leads to my broad overarching role of simulation statement. There's no perfect one, but this is the one that best captures what we're trying to do. And this was also said earlier. We want to better target and reduce the number of physical experiments during the scoping, design, and qualification stages. So that immediately takes simulation out of an adversarial relationship with experimentation, which is an absurd concept anyhow. But people, being tribal and territorial as they are, will tend to think of it that way. And of course, it's absurd to think that simulation is going to replace doing actual experiments, but it's sensible to think that you can design more intelligent experiments and that you can reduce the number of them by interspersing them with very high fidelity mechanistic simulations. Okay? So let's talk about some limitations. Lots of misunderstandings about what you can and can't know. So it was pointed out earlier, we're moving fast toward exascale computing, and people tend to exaggerate how powerful that is. And for some reason, we measure computing generations in units of 3 orders of magnitude, which sounds like a lot, but it's still finite, and it's still far from where we actually would need to be doing true first principle simulations in a lot of the subfields related to reactor modeling. Okay, so I don't want to not be excited. I'm very excited about exascale, but it's still very far from what you would actually need to carry out a complete simulation. However, even where first principles is feasible, say we are able to do routine transport calculations of a 3D core with point-wise energy values, we have the issue of uncertainty quantification, which was sort of a buzzword and a popular topic even between 15 and 5 years ago. And there's a lot of misunderstanding about what is possible to quantify and not quantify, and what uncertainty quantification it could even do or what it means. And even if you could fully solve on an infinite computer the physical laws that describe the system, you would still have a big problem. And it's a big problem that exists even for an experiment and doesn't go away. And you can't will it away with any technique or any business process that describes how you deal with UQ. And I think it's best illustrated in a classic fluid phenomenon called the drag crisis. People might have seen this before. But the idea is that the drag on a body, in this case it's a sphere in a liquid, is proportional to the velocity of the liquid that's impinging on it in this regime, and it's proportional to the square of it in this regime. So the way the coefficient's plotted, it should go down linearly here in what's known as the Stokes flow regime. Then there's some transition, and it should be constant here. And this is the drag coefficient. This is the coefficient of proportionality between the square of the velocity and the actual drag force that's exerted on the body. Okay, so this is what you expect, and you want to measure this number. Well, suddenly, when the Reynolds number, which is usually increased by increasing the velocity of the impinging fluid, reaches a critical value, the bottom falls out. And this is called the drag crisis. Okay, so suddenly, the coefficient of proportionality between the square of the velocity and the force that's impinging on the body changes dramatically, like a cliff in parameter space, okay? And there is absolutely no way any UQ technique is going to predict that. And in fact, that's not something that is a problem with a mechanistic simulation. That's a problem of very complicated physics. And you could see how if you did not know this, and you assume some kind of linear perturbation model, you would end up with a huge problem if you depended on a higher drag for some reason. Now, luckily it drops, which is usually good, but there's no simple way around this phenomenon, and you have to find it. Okay, so that's another common misunderstanding, is that, well, UQ is this very difficult field, and it's introduced entirely by the presence of simulation. So I give an example where it exists as part of the physics itself. So there are a bunch of other dichotomies that we encountered that cause all sorts of confusion. And the first one is the dichotomy between building a code and solving a problem. Okay, so if you talk to a classic, so what I put on the slide as an empirical modeler, they would say, okay, we have a phenomenon that we would like to predict, let's build a code to predict it. Okay? If you are more of a computational physicist and thinking more as a mechanistic modeler, you would say, okay, I have some phenomena or a phenomena I want to model, let's build a code. And the code will model the physics, and the physics can be applied to all these different problems. But the focus is on building the code. So you develop research programs, and the research programs are focused on building codes, not on solving problems. And there's just all sorts of confusion between these two communities and in the programs themselves about what they endeavor to do. So what I found is the best way to think about this problem is codes should be built to solve problems. I'm sorry, we should focus on solving problems. So simulation I confused myself. Simulation programs should focus on solving problems, but they can do it with an eye of generality, where as problems are solved, you accrete capability that then can be applied more generally to other problems. Okay, but simulation programs are not successful that focus on the building of a tool, except in everything I say is qualified by some exceptions, but except in very rare cases, that's a recipe for failure, okay? Focus on a problem, be able to solve the problem, accrete capability, and generalize. Next issue that I've run into is whether in trying to simulate a phenomenon, you're actually trying to learn more about the methods themselves, or you're trying to get an answer for the simulation. And it's very easy in a research environment to be unclear about what you're doing. Okay, oftentimes, you don't trust the methods enough, and you're learning more about them, and the problem is teaching you something about the methods. Sometimes the methods are very mature, and you're trying to learn something about the problems from the methods because you understand them well enough. So knowing where you're on that spectrum is critical to being able to make progress in these type of endeavors. All right, so there is the philosophy, and once all of that is straight, you can actually make some progress. And I'll lay it out for a reactor modeling problem. So here are the two approaches. On the one hand, we have empirical modeling, and I'll say that was successful on yesterday's computers, going back to the 1970s. On the far right-hand side, let's say we have supercomputers and that we can do true mechanistic modeling. A bit of an exaggeration, but let's just say it. And then let's say the reality is usually somewhere in the middle, where we have hybrid models, and we have clusters, and we have modern desktop or server, single node servers. And what we can do with each, we have to be very clear about. So one other point to never forget is a famous quote that we always remind ourselves of, and that is that if you make a plot of how much progress we've made in fundamental algorithms simply by improvements in hardware versus improvements in solver techniques, improvements in solver techniques dominates. Okay, so even if we think about solving sparse linear systems, going back to something like successive over relaxation all the way through Krylov methods, the improvements that we've gotten are actually orders of magnitude better than the improvements we've gotten from improvements in computer hardware. So it's also important to keep that in mind. So the empirical models are robust, and they are based on a lot of experimentation, a lot of calibration, and some very clever physics reasoning. And I sort of made a list for myself of the successful models that I've used over the years that are encoded in these so-called legacy codes. I guess I don't need to go through the details, but I wouldn't downplay the amount of physical insight that went into them. Their shortcoming, of course, is that they only apply to devices or to regimes that are relatively close in some parameter space to what they were calibrated for. Okay, that does not make them not useful, but it's their limitation. Okay, then in the middle, for modern desktops and clusters, we usually have some slightly generalized version where there is more physics in the codes, where we do parameterizations and collapsing of parameters, but we solve gross momentum balances and homogenized transport methods and so forth, requiring faster computers. And then there's sort of what we aimed for. So these are traditionally would have been done, and they're very accurate on that plot I showed you, but they also have very low predictive range. And what we endeavored to do was more like this. Okay, they're very, very different. And unless you can wrap your head around that, it's very hard to make sense of all of it. It has more to do with numerical solutions to governing differential equations. They could be particle methods, they could be discretizations of differential equations. So I list all of the areas in which I've done work and where large programs were sponsored. So, of course, a big one is solutions to the Navier-Stokes equation, non-homogenized transport methods. Monte Carlo transport became a very big one. Kind of comes and goes as it gets harder than we realize, and then we switch to something else which is harder than we realize. So we switch back because we like the problems with one better than the other. Now there's a phase of ray tracing that's getting very popular again. 3D finite element fuels codes informed by atomistic modeling and so forth. So, moving forward, the idea was to utilize these kind of techniques to improve these codes. Okay, it's very, very different from having these replace these kind of codes. Okay, and maybe one day now, if we're talking 30 or 40 years from now, one might have that kind of vision. Okay, so let's make it a little bit more specific. Yeah, so there's a good exemplar of exactly what I said for a particular problem. So one thing that has vexed reactor designers for years, back when we were interested in liquid metal fast breeder reactors, is what the actual effect of this helical wire wrap is on the mixing of the coolant flow that is coming through the channels of the subassembly. Okay, so one, they're used for spacers, these helical wire wraps, but they also have a significant impact on the degree of turbulent mixing of the flow. Okay, so what would you normally do? Well, people studied this problem to death experimentally, and they found relationships between things like the pitch to diameter ratio and the number of helical wire wraps and the thickness of the wire and so forth to the peak temperature and to the mixing coefficients. And they wrote codes, which I would consider to be codes on the left part of my chart, which are empirical codes, that encoded all of this knowledge, which was based off a tremendous amount of very complex experimentation, some physical insight, and a lot of quote-unquote validation, okay? So one thing that we endeavored to do, which is actually not an easy problem, is to do the numerical experiment that represents the physical experiments that went behind the development of these codes like Cobra and superenergy, using massive computers, fine-scale discretization of the Navier-Stokes equation. Of course, the problem is that you have to resolve thermal boundary layers. So you're talking a heroic problem, even to do one subassembly, where you're resolving all the way down to the viscous scales of motion, even if you do something like what's known as a large eddy simulation. Okay? So hammering on this problem for a decade, believe it or not. I mean, it seems kind of hard to believe, but we made a lot of progress on this problem. And in fact, a lot of the rules of thumb for what happened in this type of scenario, we found not to really be the case, generally speaking. And we came up with, I think, a much deeper and a broader understanding. A lot of what we did, we used to make improved subchannel codes. And a lot of what we used to look at designs that were much further from this baseline design. There were designs with the the Japanese design with a special channel at the edge. I mean, we looked at things that were much, much different from what is in a narrow range of problems that looks like this problem. Okay, so it's just one exemplar, but showing the relationship between the two ends and the importance of being clear about what you're doing, okay? How much time do I have? Is anyone keeping time? I guess, oh, no one's keeping time. Well, let's say 2 minutes? Okay, I have 2 minutes. I like that form, actually. I've never had somebody not hold a red card up by now. Okay, so when I lay everything out, again, this is conceptual, and you could argue with where I put things, but I think it's very important to have this type of mental picture of what you're doing when you endeavor to develop such a simulation program. So if we think of a continuum of methods that are developing and that we're partly doing simulations to understand the methods themselves and partly doing simulations to have them teach us something, versus sort of the other extreme, when the other extreme would probably be something like Monte Carlo neutronics, actually, where the methods are extremely mature to the point where one could argue you don't have to do much more. A lot of people would say those were solved in the 70s or 80s. I don't think that's totally true, but the point is, when you do a neutron transport simulation using a Monte Carlo method, let's say with 10 billion particles, you really are doing it to learn something about the device that you're simulating, right? You're not doing it to learn about the method itself. And I mean, you could, people do that, but that's not typically the principal goal. And each of these fields lies somewhere in this continuum, depending on what problem you're looking at and why you're doing it. And I think we have to think this way, and we have to be clear when we're doing research what the goal is and where we are in that continuum. Okay. So I'll show to conclude, I had a bunch of movies, but I wanted to make an argument for this one approach, which I think is just beautiful, and that is the idea of the blind international benchmark. Okay, because we just don't do enough of this stuff. And I attribute this to Paul Fisher and Alex Obabka and Elian Brzari. I was involved, but I didn't do this particular simulation. And that is when the international community gets together, they do an experiment, they instrument the experiment, they get the results, they hide the results, they invite everybody to do the simulation, giving you the geometric specifications of the problem, everything else you need to know. You simulate it, and you submit your quote-unquote answer, the result of your simulation. So in this case, let's say they would take a vertical slice cross-section of this pipe. Sorry, I keep hitting the wrong button. They take a cross-section of the pipe, and you take a point, let's say, or some region of the cross-section, and you look at the velocity, or say the temperature fluctuations on a thermocouple as a function of time, and you try to predict its statistical properties, maybe the variance, maybe the mean, maybe aspects of the spectrum, and you submit your results. And then everybody meets, and you're ranked, 1 through 22, which code gave results that were how accurate. So I like showing this one because one of our local homegrown codes actually won this one, and there were like 22 commercial codes that lost. Let me see if I can actually start the movie. I guess it's not clear how to start the movie from here. Well, there we go. All right, so yeah, this is actually a simulation from our submission from the NEC 5000 code, which was originally developed by Paul Fisher. So the idea is that you have a hot fluid and a cold fluid. It's really important to understand the frequency and magnitude of the velocity of the temperature fluctuations on different materials in the reactor because they determine the thermal stresses, and people want to. This is a problem all over the place, actually, not just at the T-junction of two pipes, but this is a classic problem. And so the best way for the community to move forward and to create tighter connections between experiment and simulation and to understand the limitations of our codes is with such exercises. So that's, I think, something that needs to be emphasized further moving forward. So I think I had a few other movies to show, but I think I'm probably out of time. There's no real conclusion since this is ongoing, but I'll say one thing at a very high level. In spite of all of the difficult technical challenges associated with doing advanced simulation on various aspects of nuclear energy systems, we shoot ourselves in the foot a lot by a lack of clarity of vision at a very high level, related to terminology, nomenclature, related somewhat to tribalism, and related to just a lack of common understanding of what our goals are, or what the possibilities are, and what the inherent limitations are. And I think moving forward, if we can overcome a lot of those non-technical issues, we can make even faster progress on some of the deeper technical issues. And with that, I thank you for your attention.